Now, in general, all the structures, whether it is a building or whether it is a bridge, it has a natural period. So, as per the natural period, basically, we can determine how much earthquake it shall come. So, the fundamental period of the structure as a whole, in seconds, including all the materials, may be determined by either by the regular structural analysis. It can be, we can say, eigen analysis, or it can be Rayleigh analysis also, and that is supported by, we can say, all the software, whether it is ETABS, SAP, STATS, or SAFE, or we can say SpaceGas. So with all these softwares we can find out this natural period, or if we want to cross check as per the code, this is the formula that is given for the ultimate limit state. So 1.25 times KT. Now KT is, we can say, a constant that is 0.11 for moment resisting steel frames, 0.075 for moment resisting concrete frames, 0.06 for eccentrically braced steel frames, and 0.05 for all other structures. So here we can see here that when we're talking about the steel frames, so in general, steel frames have a higher time period. So here, that is why you can see that KT is higher as compared to KT for steel frames is higher as compared to the KT value of 0.075 for moment resisting concrete frames. So after that, if you're talking about the HN is the height from the base of the structure to the uppermost seismic weight or mass in meters. Now the base shear obtained from the fundamental structure period T1 determined by regular structural analysis, the one that we have determined by the softwares, shall not be less than 70% of the value obtained with this particular formula, that is 1.25 KT HN to the power 0.75. So we can say here that if we are talking about the natural period, that is a time taken by the structure to undergo one complete cycle of oscillation. So like when we were in school, we used to study about the pendulum. So we do know that the time period for this is basically t equal to 2 pi root m by k. So moreover, the thing is same, that if here we're talking about the pendulum, but we can talk about the springs also. And in the same, we can say analogy, we can talk about the buildings also, structures also, bridges also. So it is an inherent property of the structure controlled by the mass m, stiffness k, and calculated by the formula 2 pi root m by k. Now if we're talking about the context of AS1170 part 4, so natural period of the structure is obviously, it plays a very significant role, and it depends upon the construction material, type of the structure, period of the first mode of vibration, all have an influence on the forces experienced by the structure. So in cases where a static or dynamic analysis is required, first mode natural period of vibration is calculated, and it is important because it helps us in understanding how the structure would respond to an earthquake, and also aids in designing the structure to withstand such events. So that is like the basic, we can say, introduction to the natural period calculation of the structure. After that, if you're talking about the vertical distribution of horizontal forces, now you need to understand that let us say if you're talking about this particular picture here, so we are basically calculating and applying the horizontal forces at all the levels. So that help us in, we can say, in calculation of the effect of the, we can say, this earthquake on the building or structure. So vertical distribution of earthquake forces refers to the way in which the horizontal forces are distributed vertically throughout the structure. Distribution is important because it will determines how the different part of the structure will respond to the earthquake. And in context of the equivalent lateral forces analysis, earthquake load is distributed vertically over the height of the building, and consistent with the assumption of the concentrated flow masses. How we assume that this force is basically uniformly traveled throughout this particular floor by the considering the reinforced concrete slab as the diaphragm. So by considering that only, we can consider that whatever lateral forces that we are applying or approximated loads, that it is traveled to, or we can say it is divided into all the laterally resisting frames, whether it is a column or whether it is a RCC structural wall. So how this vertical distribution can be calculated? This can calculate with the help of this particular formula. In here, basically WIHI divided by summation of WIHI multiplied with KP, Z, CH, T1, SP by mu and WT. In here, if we're talking about the this particular term, that is KFI. KFI is this particular term here. So this is basically seismic distribution factor for the ith level. That is, it changes for the all the levels. Wi is the seismic weight. Hi is the height of the level I above the base of the structure. So for this Hi shall be higher, for this Hi shall be lower. K is exponent which depends upon the fundamental natural period of the structure. So when T1 is less than or equal to 0.5, K is equal to 1. K is equal to 2 when T1 is greater than 2.5, or it is linearly interpolated. And N is equal to number of levels in the structure. So that is how we can calculate the vertical distribution of the horizontal forces. After that, we can calculate the spectral shape factor, or we can say understand the meaning of spectral shape factor CHT. Now, if we are talking about the CHT, this is the term that we are right now talking about. So let me just highlight this CH into T. So in here, if you're talking about the, basically means the spectral shape factor. So what exactly is meant by the spectral shape factor? It is a key parameter, and it is the combined multiplication factor that takes into account the site condition. How? By determining the type of the soil and the structural period of the building. So on the left, we can basically see that. So yeah, so in here you can see that basically we are right now talking about the period. So it depends upon the site condition, what exactly is the type of soil at the site, and it depends upon the time period. So we can say here that resonance of the site has large implication on the application of the ground motion, and spectral shape factor is determined from table 6.4 of AS 1170 part 4. That is this particular table, and it is used in the calculation of horizontal design spectrum CD values for a known period T. So we can see here that the equation for response spectra curves is basically given for different types of soil, and spectral shape factor CHT is simply the ordinate value in this function. So this horizontal design spectrum CD, this is basically given here. That is, here we can see that horizontal equivalent static shear force V is equal to CD into T1 into WT. So this CD itself, this is basically equal to this particular term. That is, we can say C times C bracket T1 SP by mu into multiplied with W1. In here, if we are talking about the C bracket T1, that is the value of the elastic site hazard spectrum determined from clause 6.4 using Kp appropriate for the structure, Z for the location, and fundamental natural period. So C into T1 is nothing but Kp into Z into we can say CH into T1. So CH into T1 can be calculated from this particular table, that is table 6.4. And Z is basically the site hazard spectrum factor that we already understood. Kp is the annual probability factor. So on the basis of that, we can multiply C bracket T1, and with the help of the C bracket T1, we can basically find out the value of the CD. Now, what exactly is meant by the, we can say CHT1? CHT1 that we already understood can be obtained from this particular table. WT is the seismic weight that we have already discussed in the earlier lecture. SP is the structural performance factor that we shall discuss shortly and is given in clause 6.5. Mu is the structural ductility factor. So first of all, if you want to understand the response spectrum curve here, so this is the normalized response spectra for site subsoil class. Now, there are these various terms that are given that we do need to understand before we proceed further. First of all, this response spectra is the normalized response spectra. Now that is a different, that is a difference here. Response spectra shape is a little bit different when we are not normalizing it, but when we are normalizing it, this is the shape of the response spectra. For site subsoil class, that is for soil A, this is the line that we do need to understand or refer. And for soil E, this is the line that we do need to refer. Similarly, for the other like soil class also, we can appropriately select, and on the basis of that, like on the as per the time period, let us say the building that we are considering is having a time period of 1.5 second, and the soil that we are having is soil class A. So we can simply jump onto here. So for this, we can see here that our ch bracket t1 value is equal to 0.5. So this is how we can calculate, or we can say judge the effect of the site subsoil class also, and the we can say the time period of the building. So normalized, we can say, response spectra for site subsoil class is used to represent the variation of spectral acceleration as per the natural period of vibration of the structure. So there are basically 5 soil classes: A, B, C, D, and E, that we have already discussed in the earlier lecture. So the design response spectra are obtained in the form of acceleration displacement response spectra, also called ADRS, which simultaneously indicates the acceleration force and displacement for hazard factor Z. Z is given for PGA for a return period of 500 years. And normalized response spectra are used to calculate the CHT, the one that we have calculated as 0.5. So, and that is a combined multiplication factor that takes into account the site condition and structural period of the building. So we can say here that these are the idealized representation, and actual ground motion can vary significantly from these idealized spectra. So in simple words, how this graph is formed. Basically, we superimpose like hundreds of the response spectra for different we can say site soil classes for different time period of the structures, and we do superimpose them, we do overlap them, and on the basis of that, on the basis of those rigorous, we can say, statistics, we can find out this particular shape to proceed further with the dynamic analysis. After that, these are the two important factors that you do need to understand: mu and sp. Now first of all, if we are talking about the factors here, so sp is basically the structural performance factor. So we can see here that if we are talking about the sp value, so that is basically most of the times we can see here that is less than 1. And if we are talking about the let us say for steel structures itself, so for ordinary moment resisting frames, limited ductility, the structural performance factor is high. But if we are talking about the fully ductile eccentrically braced frame, that is the best kind of steel structure for seismically active areas. So in here we can see that it is 0.67. So structural performance factor in here we can see here that is varying from, we can say, 2/3. That is, this 0.67 is 2/3, and similarly for 0.77 also. So we can see here that sp value is minimum is 0.67, maximum is 0.77. After that, if we are talking about the structural ductility factor mu, so structural ductility factor is lesser for we can say fully ductility factor mu, that is basically, we can say, 4 for the best kind of steel structure, and that is least, or we can say minimum, for the ordinary moment resisting frame, that is 2 only. Similarly for concrete structures also, if we are having special moment resisting frame, we are having the highest structural ductility factor mu. If we are having a ordinary moment resisting frame, we are having the minimum structural ductility factor, that is 2. Similarly for, we can say, limited ductile shear walls also, it is 2. For ordinary moment resisting frame in combination with limited ductility shear walls, it is again 2. So that is how we can access or check the values of mu and sp. Now if we divide mu with sp, we get one value. If we divide sp by nu, we get another value. So this is how you can calculate the values of sp by mu and mu by sp. Let us suppose if we're talking about sp by nu here, so 0.67 divided by 4 gives us 0.17, but at the same time 4 divided by 0.67 gives us 6. So that was the basic introduction to the structural ductility factor, and we can say performance factors. So if we are talking about the structural ductility factor, so structural ductility factor that we have already discussed on the left, that is basically equal to mu. So mu is before starting, we can see here that mu is basically higher for the structures which can perform, we can say, deform elastically without any significant deformation, and that is very less for, we can say, ordinary moment resisting frames. So it is a measure of structure's ability to deform inelastically. So for those structures which can deform inelastically in, we can say, without a significant loss in load carrying capacity, for them structural ductility factor mu is high. So if you're talking about, let us say, eccentrically braced frame, so for that these, mu value can be taken as 4. But if we're talking about a simple, we can say, ordinary moment resisting steel frame with a limited ductility, your mu value is equal to 2. So this factor implies the inelastic behavior, and we can see that ductility factor basically depends upon the lateral structural system implemented. System that can undergo larger deformation without collapse have a higher ductility factor. Let us say this particular example. And in the event of the earthquake, the ductility provided greatly improves the structural performance. After that, structural performance factor SP, that is a measure of expected performance of the structure. So we can see that, that is the value that depends upon obviously the type of structural system. Different structural systems have different capacities, and a building with well-detailed moment resisting frame designed to undergo large inelastic deformations would have a lower SP value than a building with a shear wall system designed primarily for the elastic behavior. So SP factor is used in conjunction with other factor to determine the design spectral shape factor, CST, the one that we have discussed a few minutes back, and is used to construct the design response spectrum for the structure. So that is like the, we can say, understanding of the SP value and mu value. So again and again, we are discussing the, let me just revise all the aspect again. First aspect that we have learned is structural ductility factor mu, structural performance factor SP. Structural ductility factor mu is less for ordinary moment resisting frame with limited ductility, and high for ductile frames with, we can say, very good ductility, or fully ductile structures. If we're talking about the structural performance factor, SP, structural performance factor, is lesser for fully ductile eccentrically, we can say, braced frames, and higher for ordinary moment resisting frame with limited ductility. This is the response spectrum curve as per AS1170 part 4, which primarily gives us this particular number, that is CH bracket T. So in the end, we do need to calculate CHT, and that depends upon the type of the soil and time period of the structure. And we have discussed that, in contrast to the graph that is given here, we are also provided this particular table. So table 6.4 is the tabular conversion of figure 6.4. So for example, let us say if we are talking about time period of 1. So for strong rock, the CH bracket T value is 0.7. So in here, we can go to the soil type A and 1. For in here, we can see that this value here is 0.7. So that is like the help that is given in the code to help us calculate the exact value of spectral shape factor, CST. Before that, we have discussed that how vertical distribution of forces can be done. So in here, there were these two parameters that we do need to understand. First parameter is the K exponent factor, which is, we can say, 1 for time period less than 0.5 and 2 for time period greater than 2.5. After that, if you're talking about the natural period of the structure, the formula that is given is 1.25 kT Hn to the power 0.75. So kT is equal to 0.11 for moment resisting frames. Hn is equal to height from base of the structure, and that needs to be, have a power, or we can say, with 0.75. So that is like the basic introduction to the earthquake analysis till now. And let us just, understand again here that earthquake ground motion shall be accounted by using one of the following. So we do have three options. To do the earthquake analysis. First option is that horizontal design response spectrum CDT, including the site hazard spectrum, can be obtained from this particular formula. So let us say we have a regular building, or we have a five floor building having 6 number of floors. For that, we usually follow with this particular approach, that is CDT is equal to CT SP divided by mu, and basically C bracket T is equal to KP into Z into CH bracket T SP multiplied divided by mu. Second option, that as per my experience is mostly done for the important projects, or it is primarily done for the industrial projects. So let us say we want to make a very big plant having 50 or 60 number of buildings. So for those particular building, it is always recommended that we do the site specific design response spectra. Site specific design response spectra means that uh, the earthquake analysis, or we can say response spectra graph, is itself made for that particular site itself. It is not referred from the figure 6.4 that is given above. So it is like referred, or we can say made by the seismologist or geologist, or we can say earthquake engineers, and that document gives us this kind of example. So let us say if your time period is 0.01, or let us say time period is 0.1 second. For that, the value given here is 0.363. Or we can see that this is one of the example of the project that I had done, and this was a very big industrial project. And ignore this, basically this is like the one that is from the other country. So in here we can see that they have shared these multiple lines. So this is the site specific spectra, and this is the spectrum that is given as per the code. So this ensures, or we can say this conveys, that sometimes it do happen that the maximum response spectra that is given as per the code also exceeds at the site. So in here you can see the clear picture that on the this particular bottom we can see that it is lesser, and on the top it is given that it is higher. So that is like the understanding that you do need to have, that it is not necessary that that site specific spectra shall always be lesser or equal to the response spectrum that is given as per the code. It can be higher also. So either it can be site specific, or it can be the ground motion time histories. So ground motion time histories are, like we can say, a question of debate only, because we do have limited information. We do have limited information of the earthquakes that we do have in Australia. Obviously, we do have a lot of information of the time histories if you're talking about the Australia, sorry, about the New Zealand, but not for the Australia. So in this, what we do is that we do have these, we can say 9 to 10 number of time histories, and we do add, or we can say upscale them as per the code, and on the basis of that we do the time history analysis. So that is like the basic understanding. And so if you are having the vertical graph also, so for that we just simply need to multiply it with 0.5. So whatever is the horizontal, we do multiply it with 0.5 to get the vertical loading. This is one of the example. So in here we are talking about the Monica earthquake. So this is the how the time history graph looks. So we do have 9 to 10 number of time histories with similar behavior of the earthquake. So on the basis of that, we can just simply do the time history analysis. After that, the question is that how many number of modes we do need to refer. So number of modes is like there should be sufficient participation, and I can say that for Australia it is only 90%. In majority of the countries it is more than 95%. And that is like the basic criteria that if you're talking about, let us say this is the example. So in here you can see that in the first mode, time period is 0.757, and the we can say the response spectrum that is happening, the participation, it is happening in RY. So it is basically 0.0814. After that, if you're talking about the second mode, the participation is happening in the X direction. If you're talking about the third mode, the participation is acting in the torsion. So in here you can see that it is 0.9226. So first mode is, we can say, translation along the y-axis. Second mode is a translation along the x-axis, and in third mode, it is the building is basically participating in the torsion. Similarly, if we go, let us say, up to the 12th mode. So for 12th mode, we can see that the participation is going up to 1 itself. So it is 100% participating. But let us say if we're talking about the sixth number of mode only. So in sixth mode, we are having 93% participation in all the three direct axes. 93 in horizontal, and for a torsional also, it is approximately 96%, 98%. So that is the basic understanding. So if for this particular example, if I had selected sixth number of mode itself, then also this clause was deemed to be satisfied. So that is like the basic understanding of the number of modes. We shall discuss that in ETABS also. But before that, you just need to understand what exactly are the significance of the clauses that are given in the code. Combining codes. So these are the various options with which we can combine either CQC, or it is SRSS, sum of root of sum of squares. Absolute is not, we use that. GMC, NRC 10%, or double sum. So most of the time either it is CQC or it is SRSS. So that is like the basic, understanding of the different number of modes. After that, if you want to read in detail about the, we can say, seismic performance of the buildings or seismic codes also, as per AS 1170 part 4. So let me just show you the document itself. So this is the code, or we can say document, a very helpful document that is written by the Australian Earthquake Engineering Society, that is given free of cost on their website. And that is basically the commentary to the code. So this is the Creative Commons license, so I can show this document to you. And this is the best document if we want to read in detail about the various aspects of the AS 1170 part 4. So I won't be going into detail, because this you can easily refer to. So from the next lecture, what we shall do is that we shall discuss the practical examples of the earthquake analysis. We shall solve various questions, so that we can understand how we can calculate the seismic forces for different types of, we can say, steel buildings or RCC buildings, or let us say different kinds of the earthquake design categories also.